In this video tutorial, we are going to discuss another shear force and bending moment diagram example problem. Here is the beam given, a beam ABCD, the 4 meter long, is overhanging by 1 meter and carries load as shown in figure. Here you can see the distributed load and the point load acting at the C point. Then draw the shear force and bending moment diagram for the beam. Okay, let's see how to solve this problem. You have to start with the free body diagram. First of all, I am going to do the free body diagram for this entire beam. Free body diagram. A point, B point, C point, and the D. Then the distributed load acting at A to B region. Here the distributed load acting. Distributed load acting. Then the point load acting at the C point. Is the point load acting. The magnitude is equal 4 kilonewton, and the magnitude of the distributed load is equal to 2 kilonewton per meter. Then here we can see two support. So I'll mark these support reactions as RB. Here another support reaction RD. In the length you can mark here 1 meter, here 1 meter length, here this length is equal to 2 meters. Okay, this is the complete free body diagram for this entire beam. And also the resultant of distributed load I will mark in a different color. It's acting at the middle. Here acting at the 0.5 length. The magnitude is equal to 2 kilonewton. Then this is the complete free body diagram for this given problem. The first thing, you should obtain unknown reaction forces. To obtain the unknown reaction forces, I am going to resolve the forces in a vertical direction. RB plus RD is equal 2 plus 4, that is equal to 6. Then I am going to take the moment around this B point. By taking the moment around this B point at 2 into 0.5, the moment produced by the distributed load. The distributed load, the resultant force acting at the middle, the 0.5 distance from the B, minus the moment produced by the point load, the 4 into 1, the distance is equal to 1, plus here the total length is 3 into RD is equal to 0. Sorry, RD is 0. In this equation, by simplifying this equation, we can easily obtain RD value, that is equal to 1 kilonewton. RD is equal to 1 kilonewton. Then by substituting this 1 kilonewton equation, the RB also we can obtain. The RB value is equal to 5 kilonewton. This is RD and RB. Then the next step, you have to divide this beam into a segment so that the loading is continuous. Here you can see, if you take A to B region, you can see distributed load is continuous throughout the length of the A to B. So you have to consider that one as separate part. And also, if you can consider a B to C region, the loading is continuous, no load, external load is acting in between B and C. Then it is discontinuous due to act of a point load at C point. Then if you consider the C to D region, there is no any external load acting, so the loading is continuous. So you have to divide this beam into 3 segments. A to B region, and B to C region and C to D region. Then you have to obtain the separate set of equations for shear force and bending moment for each and every segments. A to B region, B to C region and C to D region. Okay, then next let's see how to obtain these equations. First I am going to consider the A to B region. Let's consider A to B region. Okay, to obtain the equations for A to B region, you have to introduce imaginary cut in between A and B. So I'm going to, from x distance from the A left hand side end, here I'm going to introduce the imaginary cut somewhere in here, x distance. So then next you have to draw the free body diagram of this separated beam part, the left hand side. Here I'm going to consider the left hand side beam part. Here this is the left hand side beam part. Then you have to draw the free body diagram for this left hand side beam part. So what are the forces acting on it? Here the distributed load is acting. The intensity is equal to 2 kilonewton per meter. Then the beam part length is equal to x. Then we have to mark the shear force. This is how we are marking the shear force and the bending moment in a positive way. Okay, these are all the forces and the moment apply on this separated beam part. So then we are going to obtain the equations considering the equilibrium of this beam part. So I am going to resolve the forces in vertical directions first. By resolving the forces in vertical direction, then the resultant of this equal to minus 2x minus shear force equal to 0. Then the shear force equation, shear force is equal to minus 2x. This is how shear force is varied throughout the length of A to B. Then the shear force at x is equal to 0, the value is equal to 0. Shear force at x is equal 1 at this B point, the shear force value is equal to minus 2. Then I am going to obtain the equation for the bending moment. So to obtain the equation for the bending moment, I am going to take the moment around this A point. This is the A point. By taking the moment around this A point, here the resultant of this distributed load is acting at the middle, x divided by 2 length. So x divided by 2 minus the magnitude of the distributed load is equal to 2x into 2x minus x into shear force plus bending moment is equal to 0. Bending moment is equal to 0. So then by simplifying this equation, by taking the bending moment into subject, the bending moment equation is equal to x square plus x into shear force, x shear force into x. Bending moment is equal, here the shear force is equal to 2 minus 2 minus 2x minus 2x. So the bending moment is equal minus x square. This is how the bending moment is vary throughout the length of A to B region. So then the bending moment at x is equal to 0, the value is equal to 0. The bending moment at x is equal 1, that is equal to minus 1. Okay, then we are going to consider a B to C region. We are going to obtain the equation for B to C region. To obtain the equation for B to C region, I am going to introduce the imaginary cut in between the B and C at the x distance from the left hand side end. So then I am going to consider the left hand side beam part. So let me draw the free body diagram for this left hand side beam part. Then the distributed load is acting. And shear force, bending moment. The intensity is equal 2 kilonewton per meter, and that is acting throughout the length of 1 meter. So its magnitude is equal to, let me mark the magnitude as well, that is equal to 2 kilonewton. This is A point, this is B point. Then this is all the forces acting on this separated beam part. So then we are going to obtain set of equations for bending moment and the shear force considering the equilibrium of this separated beam part. Okay, let's obtain the shear force equation. So I am going to resolve all the forces in vertical direction. Minus 2 minus shear force. Sorry, here at the B point there's a 5 kilonewton force also acting. Okay, 5 kilonewton force also acting. Within the shear force, the plus 5 is equal to 0. Then the shear force is equal to 3 kilonewton. The shear force is a constant throughout the length of B to C region. So then next we are going to obtain the equation for bending moment. To obtain the equation for the bending moment, I am going to take the moment around this A point. By taking the moment around this A point, here this is acting at the 0.5 minus 2 into 0.5, here 5 plus 5 into 1 minus shear force into x, minus shear force into x, plus bending moment is equal to 0. Then by simplifying this equation, the bending moment is equal to shear force value is equal to 3. So 3x minus 4. This is how the bending moment is varied throughout the length of B to C region. Okay, let's find the bending moment at x is equal B point, that means x is equal 1. The bending moment is equal to minus 1. Then the bending moment at x is equal 2. That value is equal to 2. This is how bending moment is varied throughout the length of B to C region. Then let's consider the C to D region. To obtain the equations to C to D region, next we are going to obtain the equation for C to D region. To obtain the equations, I am going to introduce imaginary cut in between C and D, some n here. The x distance from the left hand side in. So then I am going to consider right hand side part. So considering obtaining the equation, considering right hand side part is easy in this case. So I'm going to consider the right hand side part. Here this is the considering element, beam part. Then what are the forces acting on it? The support reaction RD, the 1 kilonewton. Then a shear force and the bending moment that you have to mark in this way, because this is the right hand side face, and the bending moment in this way, bending moment and the shear force. So then we are ready to write the equilibrium equations. This length is equal, let me mark the length as well. Here 4 minus x, this length is equal to 4 minus x, beam part length. So then let's write the equilibrium equations. So I'm going to resolve the forces in the vertical direction. Shear force, the plus 1 is equal to 0. Then the shear force is equal to minus 1. This is how shear force is varied throughout the length of C to D region. The constant negative minus 1 kilonewton. Then let's take the moment around this. Let's take this point as O. So I'm going to take the moment around this O point to obtain the equation for bending moment. The bending moment minus the 4 minus x into 1 is equal to 0. The bending moment is equal to here minus x plus 4. This is how the bending moment is vary in C to D region. So the bending moment at x is equal 2, the value is equal to 2. The bending moment at x is equal 4, value is equal to 0. Now we have obtained all the set of equations from A to B region, B to C region, and C to D region. Now we are ready to draw the shear force diagram and the bending moment diagram. Here I have listed all the equations that we obtained for different regions, A to B region, the B to C region, and the C to D region. So then this is the loading diagram, beam loading diagram. So then the shear force diagram and the bending moment diagram we are going to draw. Okay, let me mark these regions separately. Okay, then the shear force in A to B region, how it is vary. Here this is how it is vary. It's a linearly varying, it's a negative coefficient linear equation going through the coordinate center minus 2x. So if you know the 2 points, we can draw the line, straight line. Shear force at x is equal 0, this is the value. Shear force at x is equal 1 at this B point, that's value is equal to 2. That value is equal to 2. So many here. Okay, this is how shear force is vary in A to B region. Then if you take the B to C region, how the shear force is vary, that is equal to 3 kilonewton. It's a constant value. So 3 kilonewton, it's a constant value. So here connect these two. Yes. Here you can see that because this step change because of this reaction at this B point, support reaction at this B point. So then C to D region, how shear force is vary, that is equal to minus 1. Minus 1. Okay, this is how the shear force is vary. Shear force is vary in A to D region. So then let's do the bending moment equation. Here you can see the bending moment is a minus x square. It's a parabola having maximum around symmetric around the y-axis. So its maximum value at the coordinate center. So the value is equal to 0. Symmetric around x is equal to 0. So then this is the maximum point. Then x is equal 1. That is equal to negative 1. X is equal 1. That is equal to negative 1. Somewhere here. Okay. Then this is the parabola. This is how bending moment is vary in A to B region. So then the B to C region, how it is vary? It is linearly varying. You can see positive coordinate with 3x minus 4. So if you know the 2 points, we can draw the straight line. The bending moment at x is equal 1, that is equal to negative 1 minus 1. Minus 1. Here, let me mark this point as well. 3. Sorry, this is 2, no? Yeah. Then bending moment at x is equal to 2, that value is equal to 2. Okay. Then the bending moment at C to D region, this is how it is very. It's a negative coefficient, a linear equation. It's a negative 1. So if you know the 2 points, you can mark the. We can draw the line. The x is equal to, that value is equal to here. Then x is equal 4. The bending moment goes to 0. Okay, this is how bending moment and shear force is vary. Okay, this is how shear force and bending moment is vary throughout the length of beam A to D, the shear force and the bending moment. I think you all got a very clear idea how to do the shear force and bending moment diagram for this kind of a problem. Okay, if you learn something from this video, please like the video. Okay, see you next time.